Quantum computing already makes my head spin. But get this. I was reading about some new research, and this is wild about making quantum computers even faster and more powerful. Honestly, it's got me pretty excited.
Oh, I know what you mean. Quantum computing has so much potential, and it feels like we're right on the edge of some really big breakthroughs. What research caught your eye?
It's all about building quantum computers that can handle really complex problems because right now, the bigger you make them, the harder they are to keep stable. Like, imagine trying to build a house of cards in a hurricane. That's kind of what it's like.
That's a good way to put it. Keeping those quantum states happy is tricky business. So what's the solution?
Well, that's what's so cool about this new research. They published their findings in Nature Photonics. It's dense stuff, but the gist is they're using light itself, photons, specifically to build more efficient quantum computers.
Okay, now that is interesting. I dabble a bit in photonics, so I'm curious to hear where they're going with this. Light and quantum information, there's something elegant about that combination.
It's called high-dimensional encoding.
Right, right. Instead of just the usual zeros and ones, like a light switch being on or off, they're using different properties of light. Like, think of all the different colors in a rainbow. Each one could represent a piece of quantum data.
Okay, that makes sense. More data packed into each photon. Clever. But, like, how does this actually work? Are they building tiny lasers or something?
Not quite lasers, but they've built this system with mirrors and something called a spatial light modulator. They're basically creating these, like, microscopic obstacle courses for photons, controlling their path super precisely.
Obstacle courses for light. That's wild. But, like, zooming out for a second, why should the average person care about photons doing parkour? Why is this research a big deal?
Well, for starters, speed. Quantum computers right now, they're kind of slow because it takes time to move information between different parts of the system. But with this new method, they can make adjustments to each photon almost instantly. No more communication lag.
So, faster quantum computers, that's huge. What else?
And it's not just about speed. It's about building bigger, more powerful quantum computers. This high-dimensional encoding, it's like, imagine if you had bigger Lego blocks. You could build a way more impressive castle with the same number of pieces.
And build it faster, too, because they click together instantly. I like that analogy. This is amazing stuff. But there's more to the story, isn't there? They found some even weirder possibilities.
Absolutely. While most quantum computing today relies on qubits, which, as we said, are like those on-off switches, this research delves into something called qubits.
Oh, yeah. What's the difference?
Think of qubits as even more powerful building blocks, capable of holding and processing even greater amounts of information compared to a qubit.
So we're not just upgrading our Lego set, we're getting a whole new type of Lego with even cooler possibilities.
Exactly. And the researchers actually managed to create a quantum system equivalent to 9.28 qubits, which is the largest of its kind achieved with this specific method. What's even more impressive is that it worked at a speed of 100 hertz, which is really fast for a system this complex.
That's like quantum super speed, right? So we've got bigger building blocks, faster processing, and this whole new world of qubit possibilities opening up. Where does this fit into the larger picture of quantum computing research? What are the long-term implications here?
This breakthrough signifies a crucial step towards making quantum computers more practical and accessible. Right now, they're still very much in the experimental phase. But this brings us closer to a future where quantum computers could be used to solve real-world problems that are currently beyond even our most powerful classical computers.
It's like we've been dreaming of flying cars, and this research just unveiled a working prototype.
That's a great way to put it. And like any good prototype, this research also raises important questions.
Like,
What are the limits of high-dimensional encoding? How far can we push the quantum revolution? And what other applications, beyond computing, might benefit from this level of control over light and quantum information?
it feels like we're just scratching the surface of what's possible here. This research focused on a specific type of quantum computer called a photonic quantum computer, right?
That's correct. Photonic quantum computers use photons, those particles of light we were talking about, to represent and process information.
Which is cool in itself. But from my understanding, there are other types of quantum computers being developed, like those using trapped ions or superconducting circuits. Is this breakthrough relevant to those approaches as well, or is it specific to photonics?
That's a great question. While the specific techniques used in this research are tailored for photonic quantum computing, the underlying principles, particularly this idea of high-dimensional encoding, could have broader implications.
Interesting.
In essence, it's about finding clever ways to pack more information into the fundamental building blocks of a quantum computer, regardless of whether those blocks are photons, ions, or something else entirely.
Makes sense.
So, while this research focused on light, it wouldn't surprise me if it sparked new ideas and approaches in those other quantum computing modalities as well.
So it's kind of like discovering a brand new tool. It might have been invented for a specific purpose, but its versatility could lead to innovation in all sorts of unexpected areas.
Precisely. It highlights the interconnected nature of scientific discovery and how a breakthrough in one area can send ripples of inspiration throughout the scientific community.
Now, I'm also curious about something else. The article I read mentioned something called cluster states. It sounds kind of ominous, but they're actually really important for this type of quantum computing, right?
They are. Cluster states are a special type of entangled state that are incredibly useful for measurement-based quantum computing. It's a bit like the canvas upon which the quantum computation is painted.
Okay, so the photons are like the paint carrying the information, and the cluster state is the canvas that holds it all together.
Exactly.
Right.
And the larger and more robust your cluster state, or your canvas, the more complex and intricate the quantum computations you can perform.
So this research essentially found a more efficient way to stretch that canvas to create larger and more intricate cluster states using the same amount of resources.
Exactly. They used a 50-mode spatial encoding system, which essentially means they had 50 different slots for their photons, and were able to create a cluster state equivalent to 9.28 qubits.
Wow, that's incredible. But I've got to ask, what about those spooky quantum effects everyone talks about? Things like superposition and entanglement. Are those involved in this breakthrough as well?
Oh, absolutely. They're at the heart of it all.
Really? So they're not just a side effect or something?
Remember how we talked about using different properties of light to store multiple pieces of information on a single photon? Well, it's only possible because of superposition.
Ah, right. You mean like a photon can be in multiple states at once?
A single photon can exist in a combination of multiple states, different colors in our analogy at the same time, allowing it to carry much more information than a classical bit.
Right, like a quantum coin spinning in the air simultaneously heads and tails.
Exactly. Entanglement is equally crucial. To create those large, powerful cluster states, the photons have to be entangled.
Entanglement is like that spooky action at a distance, right? Like photons connected even when they're far apart.
This means that even when they're physically separated, they're still linked in a way that's impossible, classically. It's like they can communicate instantaneously, regardless of distance.
It's mind-boggling to think about, but it's what makes quantum computing so powerful.
It really is.
Yeah.
And the fact that this research not only utilizes those effects, but also finds a way to manipulate them with greater precision and efficiency, well, it's a testament to how far we've come in our understanding of the quantum world.
This whole conversation has me thinking, if this is what we can achieve now, what will quantum computing look like in 5, 10, 20 years? What are the potential applications down the line that have scientists so excited?
Oh, the possibilities are truly mind-blowing. Imagine a world where we can design entirely new materials from the ground up, atom by atom, to create things like super-efficient solar cells or ultra-strong lightweight composites.
Sign me up for a solar-powered flying car made of that stuff.
I know, right?
Yeah.
And that's just the tip of the iceberg.
Mhm.
Quantum computers could revolutionize drug discovery, allowing us to simulate complex molecular interactions to develop new treatments for currently incurable diseases.
It's incredible to think that we might be able to tackle those grand challenges with a technology that harnesses the very strangeness of the quantum world. It all feels very sci-fi.
It does, doesn't it? And yet here we are on the cusp of making it a reality.
That's awesome. But I'm sure it's not all sunshine and rainbows.
Of course, there are still many challenges to overcome before quantum computers become as commonplace as our laptops or smartphones.
Right, right.
But this research and the sheer ingenuity behind it gives me immense hope that we're on the right track.
It's a great reminder that we're living in a time of incredible scientific discovery. Who knows what breakthroughs await us just around the corner? For now, I have to say, this deep dive into the world of high-dimensional encoding and photonic quantum computing has been nothing short of illuminating, pun very much intended.
I see what you did there.
I couldn't resist. But seriously, this research is a brilliant example of how scientists are pushing the boundaries of what's possible. And for anyone who wants to explore the technical details of this breakthrough, we've included links to the original research articles in the show notes. Be warned, they get pretty complex, but hey, maybe they'll inspire the next generation of quantum pioneers. As always, thanks for joining us on this deep dive. Until next time, keep those minds curious and those questions coming.